For question 4, it says explain activation, translocation, and beta oxidation of fat. So these are the last 3 stages of lipolysis, and so within activation, we want to bind this free fatty acid to coenzyme A to form fatty acetyl coenzyme A. And so from the last step of cellular uptake, we ended with fatty acid binding protein cytosol plus free fatty acid within the cytosol. So what happens is this enzyme embedded in the outer membrane mitochondria, the fatty acetyl coenzyme A synthetase, will activate this free fatty acid to bind with a coenzyme A to form fatty acetyl-CoA within the outer membrane of the mitochondria within the muscle. So it'll break off from this fatty acid binding protein in the cytosol and combine with a coenzyme A that is within the cytosol. From there, we will enter the translocation step, and this is where we want to move the fatty acetyl-CoA into the matrix in order to use it for beta oxidation later. So what happens is this fatty coenzyme A is in the outer membrane. This CAT1 enzyme embedded in the outer membrane is going to activate this fatty coenzyme A to enter into the cytosol. It's going to lose its coenzyme A, and it's going to add on this carnitine enzyme. The carnitine plus the free fatty acid is going to then travel from the cytosol all the way into the inner membrane, where the carnitine is going to detach from the free fatty acid, and the free fatty acid is going to enter the matrix. CAT2 is the enzyme responsible for getting rid of this carnitine and having the free fatty acid end up in the matrix, where the carnitine its job is to help the free fatty acid travel down before it is detached, and where the carnitine is left in the membrane and the free fatty acid is in the matrix. From here, free fatty acid in the matrix is going to bind to coenzyme A within the cytosol to form the fatty acid coenzyme A. Now that the fatty acid coenzyme A is in the matrix, we can go through beta oxidation. And this is where we want to cut the long chain fatty acid into 2 carbon acetyl-CoAs for Krebs. And so when we have a long chain fatty acid or a fatty acid coenzyme A that is longer than 2 carbons, we will then convert that into enolate coenzyme A through the enzyme acetyl-CoA dehydrogenase, and through this we'll have an FAD turn into an FADH2, and that FADH2 will go to the electron transport chain. The enolate coenzyme A will be converted to B-hydroxylethyl coenzyme A, I know I said that wrong, through the enzyme enolate coenzyme A hydrogenase, and we'll add water here to make that process happen. This molecule will be converted to B-keto acetylcholine through the enzyme BH acetylcholine dehydrogenase, or BHAD, and this is where NADH will be converted to NADH plus H, and that NADH plus H will also go to the electron transport chain. And then this B-keto acetylcholine will be converted to the long chain fatty acid, as well as producing 2-carbon acetylcholine through the enzyme thiolase, and coenzyme A will be added. This acetylcholine will go to the Krebs, and what happens is if these long chain fatty acids have, say, 10 carbons, it goes through the process and it produces a 2-carbon acetylcholine that leaves this long chain fatty acid of 8 carbons. That long chain fatty acid will go back up here and go through the process again, and then you'll have a 6-carbon long chain fatty acid and then another 2-carbon acetylcholine, and it'll keep going through that process. And so 3 variables that help regulate beta oxidation is when we have an increase in FADH2 and NADH plus H that inhibits BHAD, because when we have an accumulation of these, that means that they're not getting sent to the electron transport chain, which means that we're not utilizing them to resynthesize more ATP or to make more energy, which means that we don't need to keep breaking down our fuel source of fats through lipolysis, so we can inhibit that enzyme to stop this process. And in turn, it's also activated when we have an increase in FAD and NAD, because we want to convert those to FADH2 and NADH plus H to send them to the electron transport chain. It's also regulated through an increase in carbohydrate in our muscle. If we have a high carb diet, that leads to a decrease in beta oxidation, because our body uses what we give it. So when we give it a lot of carbs, we're not going to be going through lipolysis because we don't have a lot of fats to break down. And lastly, thiolase is inhibited by an increase in acetylcholine. And that makes sense because we have an increase in acetylcholine or an accumulation. We don't need to keep breaking down our fats to produce acetylcholine, so thiolase will be inhibited, and it's activated by an increase in this molecule because if we have an increase in that molecule, we want to keep going through lipolysis.